We're going to continue diagonalization. We're going to solve a few examples continued from our theory developed in the last video. So, all right. If we recall what we mean by diagonalization, then it means you want to find P and D. P is invertible matrix. In other words, has P inverse. D is diagonal matrix. So your job is to find P and D such that A is equal to P D P inverse. Then how do you find P and D? This is your job. So first job is to find D, not P. So find eigenvalues by solving characteristic equation of A. And then instead of just listing in a line, you want to put it in a diagonal entries of certain matrix and you name it as D. The second step is find eigenvectors for each lambda I. Then you have, so for lambda I, if you find Pi as its eigenvector, then put it at the ith spot of matrix, ith column. So P, the matrix P is given by P1, P2, Pn. So just side by side. Of course, the logic is here. You don't have to memorize anything like this. So diagonalization, if it is possible, then it's just two steps. The same thing as finding eigenvalue and eigenspace, but the way to arrange eigenvalues and eigenvectors are different. So you won't have D and P in this way. So this is basically from here. So the definition of the diagonalization is here, but you don't want to write in this way, but AP equal PD. And P, if you put them as each column, denote each column, then we get this relation. And at the end, you find, oh, each column is corresponding to eigenvectors of eigenvalue. All right, now next we're going to look at an example. A 2 by 2 matrix is supposed to be easy, so we can start with this. So what does it mean? So we said two steps. First step, eigenvalues. That means we want to find A minus lambda I, find eigenvalues from here. So 7 minus lambda, 1 minus lambda, 2, -4, determinant equals 0. So we have formula for 2 by 2. 7 minus lambda, 1 minus lambda corresponds AD minus BC. -4 times 2 equals 0. Just rearrange that, lambda square, and minus 8 lambda plus 7 plus 8. The minus becomes positive here, right? So we get lambda square 8 lambda plus 15 equals 0. Lambda minus 3, lambda minus 5 equals 0. So we have 3 and 5, but I'd rather write it as lambda 1 is 5, lambda 2 is 3. This is how you list eigenvalues in descending order, but for D, you won't write it into diagonal entries. This is your first job, find diagonal matrix. So if your target is find P and D, so P, D, P inverse, satisfying this. I already have this. Now, what about P? P is eigenvector. So for each lambda, so for lambda 1 equals eigenspace of 5 is going to be null space of A minus lambda I. Lambda is 5 now. And which is null space of, so 7 minus 5, 1 minus 5 means 2, 2, -4, -4. And how do you solve that? Which means you look at Gaussian elimination of this matrix, and So let me write this as I. And if you do divide by 2 for the row 1, it's 1, 1. And then multiply by 4 to eliminate the last row. So from here, your equation is x1 plus x2 equals 0. We know that this is basic variable, this is free variable, so you can move that as x1. So we can x2 move to the other side of equality. And the free variable is just copy. So x2 equals x2. Then you can write that as negative 1, 1. Good. So what is null space? Now my conclusion for this is the null space is span of negative 1, 1. Alright, the job is not finished. So we have span of negative 1, 1 as eigenspace of 5. Now for the second job, the second case, lambda 2 equals 3, I need to find the null space. So it is eigenspace of lambda 2 equals 3 is going to be null space of A minus 3I. If you compute, this is null space of 7 minus 3, 1 minus 3 is this, and 2, negative 4. And again, we look at Gaussian elimination. So the second row will be 0 automatically by adding the first row. And from first row, it is 2, 1. So we can write it as x from here. This is 2x1 plus x2 equals 0. And then that means x1 is negative 1 half x2. And x2, I just put it down because this is free variable. And then x is x2 negative 1 half 1. What is null space? Then we can immediately say this is span of negative 1 half 1. I'd rather write this multiply by 2, so scale it. Negative 1, 2. This is the same thing. All right. So at the end, we have lambda 1 equals 5 is negative 1, 1. So we have pair lambda 1 equals 5. From here we have p1 equals negative 1, 1. And lambda 2 equals 3. Then from here we have p2 equals negative 1, 2. Now the answer we can summarize. D is 5, 3. Put them along. P is put them along, but in the order of lambda 1, lambda 2. So negative 1, 1, negative 1, 2. So this is P1, this is P2. All right, this is solution. Now we turn to next example. Is A 2x2 matrix diagonalizable? Usually if the question is asked in this way, you will say no, and you are right if you say no. But why? Then we want to recall when it is diagonalizable or not. So here is necessary and sufficient condition. So if A is diagonalizable, then it has to have n many linear eigenvectors. Now we want to check how many eigenvectors are there for A. We don't care number of eigenvalues for the moment, eigenvectors. So in other words, we want to look at eigenvector, eigenspace. So if and only if it has two independent eigenvectors. So first we want to look at the eigenvalues. Determinant of a minus lambda I equals 0. Then a minus lambda I is given by 1 minus lambda, and then negative 1 minus lambda, negative 1, 1. And if you look at determinant, then this is determinant. Then we have multiply 1 minus lambda, negative 1 minus lambda, minus 1 times negative 1, which is plus 1. And here, this is lambda square minus 1, if I am correct. And here we have plus 1, so equals 0. Lambda square equals 0. So there's only one eigenvalue. So we can write lambda 1 equals 0, lambda 2 equals 0. Or you can say there's only one eigenvalue, 0, with multiplicity 2. Number 2 is, then I look like I only need to check what about eigenspace of lambda 1 equals 0. So for that we have to look at what is null space of a minus lambda I, 0I, which is null of A, null space of A. And that means null space of 1, negative 1, 1, negative 1. So Gaussian elimination, 1, 1, negative 1, negative 1. And of course, they have identical rows, so we can just subtract each other. The second row does not play any role. From here, you can write x1 minus x2 equals 0. So the solution is x1 equals x2, x2 equals x2 as free variable. And then the PVF form is x2, 1, 1. All right. There's only one independent eigenvector, or the null space has dimension 1. You cannot find two independent vectors for lambda 1 equals 0. So which means, so if you write this continued here, there's a span of just one vector. In other words, this is dimension 1. So the answer is no, because there is only one independent eigenvector. All right, that's pretty much all of it. And there's one more 3 by 3 matrix for diagonalization. I'm not going to compute that. There's nothing new, but more calculations. So again, you want to find lambda 1, lambda 2, lambda 3, and you want to find p equals p1, p2, p3. And this is diagonalizable, but the computation may be significantly longer than 2 by 2 matrix. All right, thank you.